Yeah, it's funny, just to tangent off on this for a second, I know, personally, Dave Chalmers, when he was writing his paper on the singularity, some people, uh, we won't mention names, but some people were a little bit critical that this was even like philosophy. What is he doing? He's imagining that we're going to upload, and there's a lot of weird science fiction. Some people said, look, this is not serious stuff. And I disagree. I'm on your side. I think it is serious stuff. I wrote a post on my blog about this a while ago. And the singularity, even if there's like a point oh to the infinite zero chance of it, it's one of the most significant possible events in all of human history. So we should worry about it to some extent. I think that I take that kind of reasoning serious to some extent. But also but then after he wrote that paper, which I have a short little piece as a alleged commentary on it, but it's not really a commentary. It's kind of just me, trying to jab at zombies like I like to do. But anyway, so I think people, that's part of it, is that when a well-known and well-respected philosopher writes something that's people can talk about, then it opens the door for other people to do it. And then if someone else writes a paper on the singularity, maybe someone will say, oh, it's not crazy, people are talking about this. So I think that's part of it. But if I may also spin off in another direction,
please do.
I think there's another part of it, which is that I think that we're starting to realize, and by we I mean us as investigators into the nature of the mind, we're starting to realize that computation is like maybe something like fundamental, maybe close to being fundamental. Like, so this starts with people like Turing and the beginning of mathematically formulated theories of computation and Church and those kinds of people, and Church's thesis, the Church-Turing thesis, the basic idea that every effectively computable or algorithmically computable function is Turing functionable computable. That idea that basically anything that a human can do can be done by a Turing machine. Some people think that's like pretty profound, in the sense that what that sort of points towards is, well, maybe human thinking can be captured in Turing machine notions.
Right.
And then, of course, I mean, some people, even like people like David Chalmers, who's a non-physicalist about consciousness, he still argues that computation is going to be like the fundamental notion in a psychological science.
Right.
And he gives a kind of novel and interesting account of what it means for a physical system to implement a computation. It's in terms of having these counterfactual relations, and the system has to be such that if you run it multiple times, it does things, and it's not just a one-off. And so, I think that's interesting. If it's right, it's interesting that what counts as, in order for something to be a computation, is not just causal factors about the system, but counterfactual things about the system, like what it would do if it had been in this state. Would it go into that state? So that's kind of surprising, you might say, that these counterfactuals are important. So, but nonetheless, so I mean, I'm getting too crazy here, but one of the things I think that people are realizing is that this mathematical notion of computation, which had been around for a long time but really got serious in the 30s, is playing a really fundamental role in our theory about thinking and the mind and the nature of thinking in the mind. And the more that we realize that this idea that really computation and its nature is this abstract mathematical thing, and this will bring me maybe to some work that Kripke's been recently talking about, which I really like. I was at this Kripke conference in Omaha where I presented a paper, and it was a really cool conference. Kripke himself was there, and he gave his talk where he argues that the Church-Turing thesis is basically a corollary of the Gödel completeness theorem. So that's interesting. So the basic idea is, look, Gödel has this completeness theorem that says first-order logic is complete, and then we can take any kind of computation and write out the instructions, the program basically that governs the computation. And then we can translate that program into first-order logic, and then first-order logic is complete because that's what Gödel showed us. And so now we know that the steps of the computation follow deductively from the premises of the argument, which just are the code, the instruction, basically. So if that's right, I think it is all right. I mean, that basically computation really just is a special kind of deduction. Mathematical arguments are just deductively valid arguments in first-order languages. If that's right, I mean, that's really shows how general this is, and how fundamental computation is. So you're right. There are people. The sci-fi stuff I think is important, and fiction is important. But I think a lot of it comes from this like realizing that this stuff is not just mathematical abstractions, but really has something important, usefully important, to do with the way the mind is actually doing stuff.
And one thing I would emphasize, and maybe this is just kind of emphasizing a slightly different wording, but that this is showing the power of syntactical systems. It's showing the power of merely mechanical systems. So there's one way of thinking about deductive validity is proof theoretically, so that you've got these purely syntactic operations that, of course, it will connect up to the semantical notion, right, which is completeness. But that you're going to be able to get all the semantically valid arguments via this set of syntactic procedures. And one way of thinking that about the Turing stuff is that Turing's the beauty of Turing stuff is that Turing showed that there's this set of mechanical procedures. He's thinking of mechanisms in a kind of an abstract way. He doesn't care whether the mechanism is going to be made out of wood or going to be made out of metal, or it could be made out of soul particles or ectoplasmic squiggle machines. But still, it's fundamentally there's mechanical systems that will suffice for anything mathematically decidable, anything mathematically provable. It could be arrived at by some kind of mechanical procedure.
Yes, and that's the great thing about Turing too, is that first of all he sort of gives this really nice mathematical formalization of what a computation is in terms of Turing machines. Then you realize, and then everybody is sort of realizing that all definitions of computation seems to be basically equivalent to Turing machine and sort of lambda calculus and all that stuff, blah, blah, blah. But then, and that's already like pretty cool. But then not only that, but Turing goes and builds like one of these things. Yeah. He's like, let me put some resistors and capacitors together and actually make something that does this. And then of course you get what is that? I forget the name of it. It's the Bombay or whatever, that big thing that he builds, and then obviously that culminates in the Enigma machine, which wins World War II. It's like, I mean, maybe that's a bit of an exaggeration, but
come on. Turing won World War II.
Let's just say it right now.
Let's say it. One thing I really like about Turing is this argument that he gives in his 1959 paper. This is the paper that's famous for being like the origin of the imitation game. We now know it as the Turing Test.
Yeah.
But he gives this little argument. He says, like, look, if you grant that the brain is important for human cognition, like that, what you think and your maybe also your conscious experiences, that's just like what your brain is doing, and you further make the highly plausible assumption that your brain is just finite. That one way of putting it is like, look, your brain is just made out of a finite number of particles, and there's only a finite number of ways that the particles can interact. Because of like the way chemistry works and the way valence bonding works, there's only a finite number of relevant positions that atoms can be with respect to one another. So the brain is finitely describable. It's a finite machine. It's a finite system, and therefore, whatever the brain does, it's capturable by a Turing machine. And then from there, like, it's a pretty quick argument to artificial intelligence, that we can have an artificial duplicate of Richard Brown or Pete Mandic. You get multiple realizability out of that. You get at least the first step in argument for mind uploading.
LaGuardia would love that, because I could teach like 3 times my teaching load.
We just have three of you.
3 of me, exactly. Yeah. So that I think that's really important too, and the finite bit is really important, that the brain is a finite thing.
So we're going to take a quick break. We'll be right back after the break.
I'm not sure. I'm afraid we need to use math.
It kind of reminds me, you know, I don't know how much we want to go, I mean, if we want to keep this brain-based or if we want to keep this mathematical / computational based. I like both, but, you know, this gets us back to, I don't know, I was reading recently about this debate between Hilbert and Frege. Do you know anything about this debate that these guys had? Allegedly, they wrote letters to each other, and Frege, I mean, Frege has some, like, he says some pretty funny things. He seems like kind of a dick, to be honest with you.
This is like about the logicist program in mathematics, right?
Yeah, but it's really about the idea, I guess. Well, look, I'm not. This is above my pay grade, obviously. I'm not like a logician of the first order, but or a mathematician of this stature. But I mean, from what I've been looking at, let me just give you what I think about it, and then we'll see if this is right or not. But I think probably the logicism, psychologism stuff has something to do with it. But here's the idea, that at least as far as I understood it. So David Hilbert, you know, he's the one who wants to axiomatize everything. That's one way of sort of putting Hilbert's program, is just the idea that, look, you want to provide an axiomatized system for for all mathematics, for everything. That's Hilbert's program. How do you do that? Well, he tries to do it with geometry, and he has his book called Foundations of Geometry, where he shows a method for deriving axioms for geometry. And the way he does it is by taking words. I mean, this is really complicated, but here's what, I mean, it's not that complicated once you see what he's doing, but describing it's a little bit complicated. So you take the terms that appear in Euclidean geometry, like point and line and plane, and those terms are used to define things of geometry. Like, for instance, for any 2 points on a plane, there's a straight line that connects them. That's something that you can get out of these basic definitions, and so that's a something in geometry. What he does then is to take those as like merely placeholders and to redefine them, basically. So take the term point, redefine that as like the set of prime numbers. So now point means set of prime numbers. It doesn't mean like what it means in Euclidean geometry. Now redefine plane similarly in terms of some property of the natural numbers or real numbers. And then you redefine line similarly. And then once you have them redefined in terms of the natural numbers, then you give some proof like that, you know, the set of natural numbers is going to include the set of prime numbers is going to include this number, which is prime.
Yeah.
I mean, I'm simplifying way too much here, but anyway, so you give some proof in the new redefined terms.
Yeah.
And then you go, yeah, see, okay, now I just proved that that geometry is consistent, because the proof I gave here has to be consistent.
Right.
And as far as I can tell, the reasoning is vaguely like this. If there were some contradiction, you would be able to prove it in the redefined system.
Right.
But you can't. So therefore,
Right.
the original system, which is you redefined it from, is consistent as well. There's no contradictions there. And that's called relative consistency. So that's Hilbert's kind of strategy for how you're going to axiomatize these other kinds of sciences. Whereas Frege has a different kind of approach. And you know, Frege has this really weird view that you can't just take these sentences like, you know, for every 2 points on a plane, there's a straight line that connects them. You can't just take them and redefine them, because they have they signify thoughts which are objective and mind independent, and therefore you can't change their meanings in this way. They aren't just, I mean, if you sort of zoom out, the real debate here is the debate between like a structuralist position,
Yeah.
where you just have like relations of things and you can define them however you want and then you manipulate them. And then the kind of essentialist position where you have, no, there's these things out there which are a certain way, independent of like whatever you want to. So I mean, so the way Frege would put this is that, well, you haven't proved that the axioms of geometry are consistent. You've like changed the meanings of the axioms, and then so you prove some theorem about you know, the numbers. You haven't proved a theorem about geometry.
Yeah.
Whereas Hilbert thought he was proving a theorem of geometry in this weird extended way. So what do you think about this?
Yeah, you know, I wrestle with this because there's a version of this kind of structuralism that you can describe as a set theoretic Pythagoreanism.
Yeah, I love that
You know,
stuff.
the gist of Pythagoreanism is everything is mathematical. So even rocks and trees are really just something mathematical. And one way of doing set theoretic Pythagoreanism is you start off with literally nothing, the empty set, and you throw in a little bit of set theory, and part of
By
one
the
of
way,
the
can I just correct you for a second? Because the empty set is not literally nothing.
what?
The
Well,
empty set is a thing. It's the empty set. I mean, it's a set. Sets are things.
well, yes, right. Yeah,
It has,
and
well,
further,
what are
yeah,
you
no,
talking
you're
about?
right, you're
It
right,
has power
sir.
sets and there's a
You,
whole.
you're right. Why are you still talking? You're
Okay,
right.
go ahead.
So, and another part of set theory, besides saying that the empty set is a thing, is when you're talking about, say, a set and its member or members, you're talking about two different things. So you take something, and then you take the set containing that thing. You're talking about two different things. So you've got these those are like basic ideas of set theory. You
Right,
start
but
with the
the difference is that the things are just things, but the set is a mathematical object which is defined by the membership relation.
yep,
So
right.
that the things just are out there, but the set of those things is this abstract mathematical thing which it says these things are members of the set. So that's the
Right.
fundamental notion of set theory is membership.
Yeah, I agree. So you start with the empty set, and then you have the set containing the empty set, and then you have the set containing uh, the empty set and the set containing the empty set.
Yeah,
And
you're doing power sets now.
and what you well what, one thing you're doing is you're building up numbers. So this is like the von Neumann way of constructing numbers out of sets.
Right.
Once you've got numbers, you can start talking about sets of numbers. And if you want to talk about space-time points, you can have four tuples, right? So you got a set of four numbers. These are giving you the three coordinates of spatial dimensions and one time coordinate. Now you want to start populating space-time. You want to have space-time occupants. Well, you populate it with particles. How many particles do you want? I don't know how many particles there are, but let's say there's 57. So 0 will be no particle at all, and 1 through 57 will correspond to the 57 kinds of particles. And so now we've got 5 tuples. The fifth place is reserved for the particles. And then, so now we can populate space-time points with particles. And now that we've got particles, we can start defining things. You want to define hydrogen atoms? Well, a hydrogen atom is going to be a set of spatio-temporally contiguous particles. And eventually we'll get to like your brain. What's your brain? It's just a whole bunch of particles, finite number of particles, that, like we said earlier. So your brain is a bunch of particles that are located in space-time. What it means for there to be a particle located in space-time is just to have this 5-tuple. What it means to have this 5-tuple is you've just got a whole bunch of sets of the empty set.
Yeah.
Okay, so that's set theoretic Pythagoreanism. People like even Quine has flirted with this, and I gotta say, it bothers me. And
What do you? I love it. What do you mean?
and further, it bothers me because it starts making me feel like some kind of qualiophile, right?
Yes.
Because the thing that bothers
Red,
me
baby,
about it,
the red.
I'm so conflicted, right? Because on the one hand, it's like this seems crazy. There's no qualitative differences between things. Ultimately, what's really real is the empty set, and everything is a logical construction thereof.
It's pretty cool.
And you could have an isomorphic structure that, instead of starting with the empty set and then sets thereof, starts with basketballs. So imagine a universe in which there is a single basketball. Well, in that universe, there would also be the set containing the basketball, and the set containing the set containing the basketball, et cetera, et cetera, et cetera. Now, according to this this relationalism, there's really no difference between the two universes. They would be structurally the same.
Right.
The basketball universe would still have Richard Brown in it. It would have Richard Brown's brain, et cetera, et cetera. But isn't there a difference between the empty set universe and the basketball universe? Isn't there some kind of like qualitative difference? Part of me says like it's not, this is not good enough. There has to be some kind of like fundamental elements that aren't the empty set. And
well, I mean, look, but it's true, what your argument suggests is that there has to be an element. But if the empty set is a thing, then that's about as as you get. It's the ultimate thing. It's the empty set. It's not nothing. That's something else. That's you know, the extension of the empty set. The empty set has no extension. But the empty set itself is a thing that contains this other thing.
But one way of describing this this empty set construction is that there's no intrinsic properties, or the only intrinsic property is like the intrinsic property of being the empty set, and everything else is purely relational. And if you do have qualiophile intuitions, and I'll admit that I sometimes have those intuitions, there's something kind of disturbing about this lack of qualitativeness.
Be not disturbed, young Skywalker, because, you know, so this gets us to the, you know, Russellian monism and a lot of these kinds of issues. We're kind of moving away from the reason I invoked Hilbert Frege, but that's fine. I mean, I was going to talk about finitary methods versus infinite things, and
I'd be happy to get back to that too.
Right, yeah, because I was going to talk about Hilbert's complaints that, you know, against Cantor's progression of infinities.
Oh, I definitely want to talk about that.
And especially Hilbert's idea that that there's a special prized section of mathematics which is finitary. All the stuff that we talk about, finite stuff, that's somehow special. And then that sort of, I think connects up to this Turing idea you were just talking about, that the brain is a finite system. But so let's put a pin in that, because let's continue
I'm writing
talking
down
about
Cantor and Hilbert, because I definitely want to get back to those guys.
Yeah, and it connects to this Frege stuff. But you're right. So the issue here is whether you can have just a system of relations without something that's fundamentally being related.
Yeah.
So in the set theoretic Pythagoreanism stuff, you know, you have just the empty set. That sounds about as close to nothing as you can get, but it's not really nothing. It's something. It's a set.
Right.
It's a mathematical object. And so if you have something, you could build other things. You don't get. It's not like getting something from nothing.
Fair enough.
So no, but maybe you want basketballs there. That's fine.
Right.
And maybe you could put, you know, qualia there. That's, you know, I guess that's what Chalmers' idea and Galen Strawson's idea is, that, you know, the thing that's grounding all the structure are these, fundamental qualitative properties like phenomenal red, phenomenal green, maybe phenomenal pain. I mean, I don't know. It's hard to, when you press them on the details, they say, who knows, really, but they're still working on it, and that's one of the exciting areas right now, is to see them develop this reductio. No, just kidding. Just kidding. Because you know what? I mean, to be fair, I do think that ultimately, if you take that view, so let's say you do take this view. You have the structures, and you define it however you want. I like empty sets, and so you say, but what's underneath all that? Okay, well, there's qualia. Now you ask yourself, well, are the qualia physical or not? Well, I think that by the time you've done that, you've entered verbal territory.
Yep.
Answer to the question, are those qualia now physical or not, is purely 1,000% verbal. So if that turned out to be true, I would say, you know, the analogy for me is always magnetism and electromagnetism in particular, and the field in particular. And you look back at history and you find these people, and they're just like saying, look, fields, what are you talking about? That's crazy. How could there be this unextended thing? I mean, it seems extended. Yeah, it takes up all of space-time, and there's a value for it. It's never non-zero. It's like sometimes arbitrarily close to zero, but there's always a value for it. Even infinitely far away, there's a value for the gravitational field of Earth. I was like, what? That sounds so weird. But you can't do physics without it. It's firmly entrenched, and so they just said, you know what? Fuck it. It's a fundamental feature of reality. And now we have quantum field theory. Bam. So sometimes when you do something like you can't, and the basic strategy is when you find something you can't do without, but which doesn't fit into your theoretical structure, you add it as a fundamental feature, and then you go on with your life. And that's happened like so many times. You know, we could just look back over and over. It's happened. Negative numbers. for instance, people said, negative numbers, what are you talking about? That's insane. No, we can't do without them. Oh, atom, negative numbers, boom. Imaginary numbers, what? That's crazy. Not on the real number line. Where are they? Okay, so blah, blah. Trans-infinite numbers. By the way, I was reading some about this recently, and Cantor, I never quite thought of it this way, but one of the really super interesting things is that Cantor proves that there are, uncountable infinite sets. That's the technical language, but anyway, that the number of real numbers is greater than the number of whole numbers or whatever.
Yeah.
But he does it without ever providing one example. He doesn't ever show you one of these numbers. He just always says, there's more numbers than any given list of the numbers you think is complete. So I thought that was interesting. He never provides an example. But anyway, so if you take that kind of view that there's those things here, that's my point, is that that's a verbal issue because at this point you can just appeal to the magnetism stuff and say, look, consciousness, we can't do without it. We're not going to be Dan Dennett and say things that are literally absurd. So we're going to keep our wits. We're going to keep our wits about ourselves.
Wait a minute, buddy.
Sorry, but it's true. We're going to keep our wits about ourselves, and consciousness is non-negotiable. Like we're not going to negotiate about consciousness. It's there. If you really can't fit it into the science that we have, which is this functional, structural, kind of relational business, then the only reasonable option is to add it as a fundamental entity. Like I'm fully on board with that being the only reasonable alternative. I just don't buy the second claim there that you can't fit it into the structural, functional stuff. So I think that even in the empty set world, where it's just like constructions out of the empty set, you're going to get consciousness, and that's because if this is that world, then what we call biology just really is constructions out of the empty set. So I'm happy with that being okay, as long as some brains are involved, and as long as brains are constructed out of the empty set, and as long as it's my brain being in various states that makes it the case that there are certain things that it's like for me to feel various things. Then whatever the fundamental nature of the brain is, that's physics. That's fine with me.
But so you, I think, agree with Dennett and I that qualia aren't going to be some fundamental thing, some fundamental intrinsic property.
I agree with Dennett and you that we don't know that it is. But it could be. I mean, it's a legitimate, open possibility that consciousness is fundamental. So I think the difference between someone like me, who's a qualia realist but also an optimist, and someone like Chalmers, who's a qualia realist but a pessimist, is that we're qualia. We have qualia. We know it, and we're not going to negotiate about that. And if that means if you can't weasel your way out, and if you don't think science is going to help, then there's no other option except fundamental added in. Because by the way, same with electromagnetism. No one's going to get rid of electromagnetism once we have the equations and once we see. I mean, you can't do without it. So you have to add it in as a fundamental thing. Then you see how useful it is and what you can do with it. And so now it hangs around.
But just to clarify what your optimism is, you're optimistic that we can explain consciousness in terms of stuff that's not conscious.
Well, no.
For example, we can explain what water is, and the explanans will make reference to things that are individually not water.
Right. So, but see, hold on. So it depends on what you mean by explain. So my optimism includes, the 1,000 flowers blooming kind of optimism. I'm not hedged. I don't feel like I'm committed to any single particular view about this here. What I think is that there's a lot of them, and they all any one of them at this point might be the one that works. None of them have really been definitively ruled out. So, and I would compare this to what Quine tries to do, but he doesn't do it as well, in my opinion, when he writes Word and Object. And he basically tries to show, look, behaviorism can do most of the stuff that people think it can't do. And then everyone afterwards said, oh, he's a fucking behaviorist. And no, maybe he wasn't. He just said, look, the physicalists can say something about this stuff. And by the way, 50,000 years from now, who knows what we'll say. But right now, we can use these tools and say this about it. And so I want to have that kind of attitude that, we have some tools around.
Yeah.
and some of those tools look promising, and they haven't been refuted by any a priori reasoning. There's no like definitive refutation of them. They haven't been shown to be inconsistent with science. There's no scientific refutation of them. So therefore, they're open possibilities. But that's all that they are, is open possibilities.
Right.
And on the table, along with those open possibilities, are also fundamentalism
Okay.
and epiphenomenalism. And epiphenomenalism is like, if that's true, then,
Right.
life sucks. But if it's true, it's true. And fundamentalism is like, if that's true, then life is really weird. But if it's true, it's true. But I think that the important area is these other two areas, where we don't know that they're false. And one of the important options is that you can't explain it. So that's why I was hedging and saying, oh, no, is because, yes, one of the options that's open is, yes, we can give an explanation. And I have a story about how that would go. It's roughly like similar to the kind of story that Chalmers tells, except for that you put qualia optimism in place of qualia pessimism. And so, yeah, I think that you could be a rationalist in the 2Dist semantics and all that stuff and still think that, this stuff works and that ideal reasoners could come to know about consciousness just based on physical facts. So I think that's totally possible. But I also think it's possible that, someone who thinks that identities don't get explained could be right, and that there just are these brute identities in nature. And water is H2O might be one of them, and you don't explain them, but you use them to explain other things. That's one way of taking Ned Block's view, is that water is H2O doesn't get explained. You posit it as fundamental. See, again, this fundamental. Posit it as fundamental, and then use that to explain a bunch of other stuff which you want.
Well,
both of those seem like live options to me.
What bothers me.
Oh, and by the way, just to wrap it all up. And also structuralism seems like a real option to me. Of the real hardcore, like Ladyman and Ross, structuralism, like, all there is the empty sense structuralism. I think that's a live option too.
Yeah.
So I don't think any of these have been refuted.
So we're going to have to wrap things up for this episode, but we are going to continue the discussion in our next episode, and we're going to focus there on the question of what the nature of explanation is.
I'm Richard Brown, Associate Professor of Philosophy at CUNY LaGuardia, here for Space-Time Mind.
That's gold. You're a star.
All right.
And I'm Pete Mandick from William Patterson University. You've been listening to the podcast Space-Time Mind. Our musical theme is provided by the band Quiet Karate Reflex, a band that Richard and I are both members of, along with Hakwan Lau and Alex Kiefer. And the name of the song is Aristotelian Eye Jelly. Until next time, we'll see you in space-time.